Hello guys, welcome back to a new video of the series. Last time we've looked at our serial logger, and we've also fixed an issue that we had on our stack setup. Today we are going to look at some basic mechanism that we can use to allocate heap memory this early on in our kernel. The problem with heap allocation is that we do have a sort of chicken and egg situation here, where we need to allocate memory to write an efficient heap allocator, but to allocate memory we do need a heap allocator, right? The way we went around this problem here in our boot loaders, especially the BIOS one, is by just postulating that we know that some bits of memory, so I think we should go to start.asm. Yeah, there we go. So we postulated that we have bits of memory that we know that are reserved. We went with this sort of convention, which is pretty okay if we have a few allocations. But as we start allocating more and more, we might find ourselves doing some weird stuff with that. So convention is just not going to quite cut it here for our needs. So we are going to need to be a bit more clever about this. So let's get right into it. And so the vision I have for this heap stuff is that we are going to create a first allocator, or we are going to create a an allocators chain, where basically we do have an early allocator that will allow us to allocate some memory from a small pool, from a small heap, and we are going to use that allocator to bootstrap a larger, more efficient allocator that is going to allow us to allocate memory more efficiently, but also that will need to have, I guess, more complex data structures in place to do that. So we are going to need to allocate those on the heap somewhere. Right, so the vision, let's get back to that. The vision is to create, let's call this heap.sig, and let's start with allocating the very first early allocator. So let's first import stud, or do we need, I don't think we need stud. Yeah, I don't think we need stud. So the idea for this allocator here, after quite a bit of thought, is that we are going to create a variable, just a buffer, an array. Let's call it kernel heap, and this will have so some size. Let's call it max. Let's call it kernel heap size, and this will be a U8, just a bytes buffer, and we are going to initialize that. Actually, we can just initialize that right from the start, I think. And we are going to initialize that with a bunch of zeros. So kernel, oops. There we go. Kernel heap size. Right, so we are going to need to define kernel heap size. So kernel heap size is, let's go for 1 meg, I guess. So 124. Right, and my thought process is that this kernel heap here will be disposable. So once we initialize everything that we need to initialize, we can just get rid of this kernel heap. So I think we are going to need to create a secondary heap that will not be disposable. It will be permanent. And actually, let's call this one permanent heap size. And let's call this one kernel heap. So this one is the disposable one. So permanent heap size. So this one here will be permanent kernel heap size. Same for this, permanent kernel heap size. Right, so now we do have two heaps, one that's fairly small, 1 meg. We can actually go lower than that, depending on our use, but this one here will not support any deallocation. So everything that we want to keep during the whole runtime of our kernel will go here. And this one here will be a bunch of temporaries. So anything that we can actually get rid of once we have another heap allocator running. Right, so I guess we could do something like const, so permanent alloc, and this one here will be so stud, I guess stud mem. So I guess we do need stud here. So const stud is import stud, and we are going to do so fixed buffer. Is it in our heap? Fixed buffer allocator, right? And we are going to initialize it with our permanent heap. There we go. And we are going to do pretty much the same here. So permanent goes to kernel. Kernel. There we go. There we go. Right. So now that we have these two allocators, we are going to need to somehow give them out to our clients, quote unquote clients. So anyone that will need to allocate something. So I guess we are going to do permanent allocator as a function that will return allocator. And I guess allocator will come from stud allocator is stud mem allocator. There we go. So, and in here, I think we are just going to do permanent alloc dot allocator, I think. Does this fail? No, it does not. Okay, cool. So I guess we are going to do the same thing here. Let's call this just allocator. And as allocator. There we go. And here is kernel alloc dot allocator. Cool. Right. Okay, that's pretty okay. That looks okay. Now, the main issue that we have is we kind of want our heaps here to be somewhere we know they are, so we can just ask our basically we don't want this to be initialized with zeros at runtime. We want this to be initialized by zeros when our bootloader loads our kernel. So that's basically what we did here. So if I go to BSS, so we check if our segment here is a BSS segment. And if it is, then we basically memset it to zeros. So we do have this functionality here in our bootloader, so let's not do it again in our kernel. Right, so the way I'm gonna force that, because I think that with some luck, with quite a bit of luck, we can count on LLVM doing that for us. But I'm going to try to force the issue just to see that we can do that. So I'm going to set a link section here for our heaps, and I'll call that, let's call it kernel heap. And I guess link section should come after the type expression. Can we do something like this? I guess we can. Right, so we should remove those, and I guess he's not happy for some reason. Right, okay, so let's change these around, I guess. We should do something like this, and we should do something like this. There we go. Same thing goes for this one here. So this would need that, into a link section. That's pretty much the same. So kernel heap. And here we should remove this and this. Cool. Right, so now that we have these two things here, we can actually go ahead and take a look at our linker script. Actually, let me just do depstop equals 2 just to align everything up. And we can go ahead and, you know what, I'm gonna do a bit of cleanup here. Yeah, okay. Yeah, let's clean these things up. And actually, I've already seen this section here, kernel heap. That's why we used it. And it's set in BSS. So BSS is the section that's marked as, basically it's marked no bits. So basically it has nothing written in it. It just has information about the sizes that it wants to be once it's loaded to memory. So we expect the bootloader to just take a look at this section here, see that it has a size that's different from its size on file, and allocate that size in memory and set it to zeros. That's the idea here, at least. So now let's go back to heap. We set up our link sections. We set up our, and actually since we expect our memory to actually be zeros anyway, so let's do undefined here. So undefined, and of course I can never type undefined. Right, so now that we have these, I guess we can go to main and try to use them for something. So let's create a var list. I will do stud array list of some type. Let's say u32s and init, which takes an allocator. So let's call it alloc. Of course, here we are going to need const alloc is so heap dot allocator. Of course, we need to import heap. So at import heap.zig. There we go. So 24 down. List is not used, so let's use list. So append some numbers to it, I guess. Yeah, let's append some numbers to it. Let's do something like this. And I guess we should see that we have the correct numbers. So for list.items, we get that as item, and we do set log info of, I guess we could do something like this. Oops, there we go. And we can do something like item D is equal to D. And here we'll have I and item. There we go. So let's build this and see everywhere we kind of made a mess. So self-fix buffer allocator error union is ignored. Right, so it's in append. I guess append does fail. Right, so here's what I'm going to do. I'm going to do failable main with catch, I guess. Yes, okay. And I guess I'm gonna catch whatever error is comes from that, and I'm gonna do log.error failed with error, and I guess just do something like this for now, and here we can do something like that. And here I'm gonna do public failable main, and this one here cell takes no arguments, and it returns I guess some error or void, and inside that we are going to get our thingies, and of course here we are going to just try these things. So what's the problem here? Expected function, of course, needs this, and that should make our compiler pretty happy. It's not. Cast discards const qualifier. Where is that? That's in kernel. Oh, okay. So that should be in heap, and that means that this one here cannot be const. That's fine by me. Right, what's the issue here? Value of type mem allocator ignored. What do you mean? Oh. Okay. Pretty normal stuff. Okay, it builds. So let's first run it and see that it prints out some numbers. Okay, that's pretty cool. So we do have a fairly early allocator working. Let's dive a bit deeper into what we wanted to do. So let's do read elf dash all and kernel 64.elf. And right, so let me do something first. I want to run this as so release is fast. I want the fastest release, and I also want I guess some things here were dropped. Why? So what do I want to remove? I guess this one I don't want, and I want to omit frame pointers, and I even might want to strip the binary or the debug information from the binary for now. I could actually do a check. Probably should do a check. So if optimize, or maybe do I switch on it? Switch on optimize. So what are my okay, so if I have debug I do kernel exe dot module root module dot optimize no dot strip is false. Right, and for anything else, actually else, I want this to be strip. Right. So that means that I don't need to set that there, and that should be okay. So let me rerun this. So it's really fast. It should be stripped. Let's reread the elf. Cool. It has no debug symbols in there. Now let's go back to just a normal debug build, and we have our symbols back. Cool. So just going to try to do this. Let's build it again. Let's clear this and try to read the elves. Right. So here I can see that BSS is okay, so we do have a bit of an issue, I think. Wait, hold on. So in segment 2, we should have data and BSS. That's actually not really great because now BSS is marked as prog bits. We want BSS to be marked as no bits. So we want it to be zero initialized by the loader, and not have all those zeros on our binary, because I guess let's take a look at, so if I do something like this, let's take a look at how big our binary is. We can see that our binary is enormous because we have all 4 megs of zeros of heap memory inside our ELF file. So just a bunch of zeros written there, which is what we wanted to avoid in the first place. So how can we go around that? Let's see here. So we do have this. We have this equals to undefined. So this should be okay, I think. And you would notice that we only have 4 megs in there because we haven't used our permanent allocator. So if we go back to main, if we go back here and we do pretty much the same thing, let me just copy this and do so perm alloc, and here we do permanent allocator, and here we do perm alloc, and we just name this something else. List 2 goes here too, and this goes here too. Yeah, so now if we build this, we should see that our file actually gained an extra meg of data because we are still putting all of our BSS as prog bits, and it's actually allocating huge amounts of basically it's storing a huge amount of zeros on our file, which is what we want to avoid. I know that disk space is pretty cheap, but we are working on a kernel project, not a web application. So a few megabytes of zeros are actually a big deal for us. Right, so let me try something here. I'm going to create a new heap section. and I'm going to put, so let me just remove that here, put that here, probably bring this to, right, so now we have our heap section here that's separated from our BSS section. And now we can see that our BSS goes back to no bits, whereas heap is actually containing something. That means that our program is trying to be smart with our heap here. So that's something we are going to have to deal with. So how do we force the issue? Actually, let's go from this to this, just for this one, permanent heap size. And let me just see if we can spot any differences. Okay, so it still has some bits in there. Let me try something else. Let me try to remove this link section here. And of course, we need to build it. Right, so here we can see that in BSS, we gained 1 meg, so it's 0x 100,000 in hex. That's 1 meg. And here we can see that in heap, we still have our 4 megs of kernel heap. And those are marked as prog bits. So for some reason, let me just put this back in there, try to do something like this. This is kernel heap size. Let's try to see what's going on. So we still have the same issue there. I'm not sure what this is doing. So can we do something like I don't want to force the issue by putting this as external and defining it in our kernel script. That's not going to help anyone, I think. So what am I going to do? Can I force... just want to make sure that we are using our linker script correctly. So let's see if this makes any change. No changes there. Right, so what can we do about this? We know that if we just let it choose without us knowing which linkers or link section we are going to, it's going to put it in BSS. But if we don't let it choose, if we force the issue ourselves, it's going to try to put it somewhere else. And actually, I want to try something else. If I put this as undefined, but not set a link section, how does it handle that? Right, so it still goes into BSS. So I guess the undefined is actually pretty okay. Now, the other question is what happens if we put this back into BSS? Yeah, no. Actually, what I'm going to do is I'm going to try to force the issue here by setting this as no load. And we'll see what we get. Right, so now this one is marked as no bits also, but I'm not sure if it's actually. Let's do something before we do the no load stuff. Let's take a look. Let's try to dump that section and take a look at what it contains. Actually, hold on. Right. That's kind of weird. So let's try it again. Right. So let's LVM, I guess, obj dump and headers for, let's add this for build kernel 64.elf. Of course, and this one is marked as data for some reason. Right. So let's just dump the whole thing, and we are going to try to take a look at what we have there. So yeah, so this means that it's just a bunch of zeros. Now the question is, why is LVM putting a bunch of zeros as data? Okay, so for some reason that does not work. So let's go back to this here. Actually, I'm just gonna try something. Not try something, but make sure that all our sections are page line, so that our bootloader works. So these ones are page aligned. These ones too. Actually, I could just do something like this. Align 4K. I don't need this. Same here. Can just do something like this and get rid of that. And same goes here. We can just align it to 4K, 4K, and remove that. We also want this especially to be aligned to 4K. So that's okay. Here we have kernel and is aligned to 4 bytes twice for some reason. Just gonna have this aligned to 8 bytes since we are on x64. That would look a bit better, I think. Right, so let's take a look at this. So now BSS is marked as data for some reason. I guess something between the Zig compiler and the LVM codegen is not like in our little link section here. Yeah, so it still identifies BSS as data basically, which is not good, not great. Actually, can we force the issue by setting this to const? And I guess here we are going to need to const cast this. Great. Right. Actually, let me just set one of those. Yeah, let's set both of them. Const cast. Do this, do that. There we go. Make. And let's take a look at what we have here. So we still have BSS as data. So the const did not is not enough, basically. I guess this is not really something that we need to do. Does this force anything? No. No. Okay. Well, that's not great. Okay, so I guess we don't have a choice. We are going to, at least until I figure out some sort of a better line, a better solution for this, we are going to just stick with having our kernel heap somewhere here. We are going to force it to be a no load section, and expected right. So I guess this should go at the very end. Okay, and now we do have a heap which is set as BSS, but now BSS is still set as data for some reason. Oh, of course. Of course. Cool. So now we do have both heap and BSS behaving correctly. So if we do a little build, we can see that our kernel is now just 21 kilobytes instead of 5 megabytes, which is always a welcome change. Well, with that, our early allocator is done. It's working. We've tested it. And now we are going to... actually, I'm not going to mark it as done just yet. I'm going to think about how we can actually try to start working on some of these allocators. So I'm just marking this as pending here because I'm pretty sure we are going to have to come back to it. But at least for now, we are able to move on to some other things if we so choose to do. Well, that's pretty much it for this one. As always, if you liked it, hit like, subscribe, leave a comment if you have remarks or questions. Speaking of questions, you can also ask them in the Discord. I'm trying to become a bit more active on there, and until the next time, I'll see ya. Fucking out.